Hello, everyone, and welcome to our seminar of this week. This week, our presentation is going to be about permeability measurement in low permeability rocks, approaches, challenges, and solutions. And for today's talks, we have as a presenter, Dr. Nathan Deisman. And there are some co-authors of this work, specifically Dr. Talman, which is here, Engineer Guerrero, Master Guerrero, which is here, and Dr. Chalaturnyk, which is not here. Now, and a little introduction of today. This work will present an exploration into the use of the transient pulse decay method for measuring permeability and specific storage in low permeability rocks. We will investigate why this method is important and what it may offer in terms of understanding hydraulic properties. Our presentation starts with a comparative analysis of approaches to solving the differential equations for transient pulse application. We will look at the assumptions at value of the common analytical solutions of Brace and Hsieh. Special attention will be given to the use of differential pressure measurements and the application of upstream and downstream pressure measurements in their implications in various experimental configurations. We will discuss crucial aspects of the testing configuration and specimen loading, including sample preparation, specimen dry, resaturation, the impacts of test condition on sensors, and their implications on the measurements and permeability solutions. Also, common problems such as sample homogeneity, leaks, temperature stability, and issues associated with extreme low permeability, such as the impact of poroelastic waves, will be addressed. Furthermore, we will present new approaches for the solution of the transient pulse decay to account for imperfect experimental systems through the leaky brave and leaky Hsieh model, how we use them, and the potential for interpretation errors. Throughout the presentation, we will show results for a completed testing program on granite with permeabilities ranging from 1 to the power of negative 90 square meters to 1 to the power of negative 22 square meters, tested using isotropic configuration stress up to 30 megapascal and 40 Celsius. Based on our learning and experience results from this program, we will present our optimized pulse decay measurement system designed on build, including our approaches for depth volume optimization, efficient data logging system, and effective sensor selection and placement. For this talk, we have with us Dr. Nathan Deisman, who is a research associate in Professor Chalaturnyk's research geomechanics research group, reservoir geomechanics research group. He started in the group in 2002 and has worked in the field laboratory on numerical simulation. His projects include core retrieval from remote locations, downhole tools development, and deploy for nuclear waste and CO2 storage, laboratory testing of oil sands, coal, shale, sandstones, and hard rocks, and numerical simulation using Itasca PFC and FLAG 3D and CNGs to solve geotechnical and coupled THM problems. So join me welcoming Dr. Nathan.
I guess I should have edited that. That was basically everything. So before I get started, I'd like to first acknowledge that the University of Alberta is on Treaty 6 territory, and that we should work together to come to understanding of how the treaties have impacted our Indigenous friends and colleagues. And the other thing I'd like to say is I just had a long talk with a very good friend of mine who has personally been affected by the war between Gaza and Israel right now. And it's important to recognize hate speech, both on people who are supporting Palestinians' resistance and Israel's right to defend themselves, and that the killing of civilians hopefully will stop as quickly as possible, and that everybody can get on to live in peace. But as I said, it's important that everybody recognizes what hate speech looks like. Hate speech looks like on campus, and if you wish to demonstrate, do it peacefully and in a manner which is respecting everybody and not putting people at risk. So that being said, permeability measurements in low permeability rocks, approaches, challenges, and solutions. So this is some work that we had started doing for NWMO, Nuclear Waste Management Ontario. They're looking to site a nuclear waste repository in Granite. And the dot there is the Google map location of a place called Ignace. Oh, you do that, yeah. And if you want to see the detailed report, it's all public. So the data that I'm showing has already been published and is publicly available. So just some numbers to get a range of what we're dealing with. If you're in nanodarcy, I put it in nanodarcy because that was the audience I was presenting to, but we're down at minus 20, minus 21 meters per meter squared, minus 14, minus 15 meters per second for permeability measurements. And you can see just some data from that report. The porosity for this particular work is ranging around 0.5 up to 2.5%. We measured that doing like completely drying the specimen, helium porosity, and then also through grain density crushing, and then through water loss porosity. So each of those measurements slightly different approaches, looking slightly different permeability or porosity measurement techniques, and accessing more or less pore connectivity. So generally two types of techniques to measure permeability. One is through steady state measurement, very commonly done. Darcy's law, we do it all the time in geotech, or a transient permeability approach, which is a technique that you need to apply if your permeability is getting down quite low, where you can't measure volumes in an appropriate time scale. So steady state, obviously, we should all know this one. Apply a constant flow rate or a constant delta P, run until delta P or your flow rate is constant, and then use that to interpret permeability. Usually you're using a delta P, so you put a delta P transducer across that, or you can use an upstream and downstream pressure transducer and take the difference. In low permeability, the time to reach steady state can be appreciable, and you must get to steady state to get some results using that approach. The approach I'm going to talk about today is the transient approach. So you establish a pore pressure inside your specimen, constant pore pressure at some effective stress state, and then you apply a delta P on the upstream or downstream. That delta P can be a positive or negative, just a pressure transient. And then you monitor the pressure decay and build up on the top and bottom of the specimen, depending on how you apply that. So that decay curve is characteristic of both permeability and sample storage, or test system storage as well. I'll talk about that. You can do a faster test than steady state, and you do not need, the test does not need to run to completion to extract results. So you don't have to wait for the pulse to completely come to equilibrium. You can get data from partial results. So permeability is generally determined by steady state. So I talked about this, but if the permeability is low, that measurement time may be quite long. And I have some diagrams on the side, and permeability and microdarcy. and nanodarcy. So I just plotted the time to collect 1 milliliter of fluid in a specimen that's 61 by 61 versus permeability. So 2.5 inch by 2.5 inch. And you can see that as your permeability decreases, you start to come up onto like days worth of time to collect a small volume. What's the problem? The big problem with most experimental testing of very low numbers, permeability, maybe even mechanical properties, is small temperature changes in your testing system can completely impact what you're trying to do. So the transient approach, that issue is avoided because we're shortening that measurement time and therefore reducing the length of time that temperature can possibly occur. A transient or a change in temperature in your system environment can impact your test. So just a simple calculation and I'd recommend this for anybody doing any sort of laboratory testing, is just put a temperature probe in your laboratory and attach that to your data logger and monitor the temperature of your test and include that in your experimental results. So this was some data just taken from a temperature test that I think Hsieh was running, or a permeability test Hsieh was running in steady state. And this is the temperature in our laboratory up on the 5th floor of NREF. So it's changing by, once the test gets going, plus minus 0.5 degree. So you do a simple calculation using thermal expansion of fluid, and you can see that you can introduce some large pressure transients inside of your test. Now, obviously, it's not perfectly correlated to what's going on in your specimen, but it gives you an idea that pressure is going to fluctuate inside of your specimen if you're trying to run a steady state test. Your boundary conditions will probably mask this, and you'll never see that if you're running a constant flow or constant pressure system. Another example, you can see this would just be to set up a test, and this is some real data from steady state. Delta P is in the green dotted lines. The solid line is just the flow volume, and then with time, so it gives you the flow rate or cumulative volume on the axis here. So the flow, you can use that to get flow rate, and then you look at it and say, in this period, I can find a window where my temperature is stable and my pressure, delta P, looks pretty stable. But if I start to move or look at the data where my delta P is, or my temperature is changing, my delta P is going crazy. So you can see all these transients being introduced or changes due to temperature. This one, permeability is 4 millidarcy, so relatively low, but in the numbers that we're trying to get, pretty high. So that's just a review on steady state. Pulse decay. You bring the specimen to equilibrium in your cell, so you can apply confining stress, pore pressure. We'll talk about saturation in a second. And you create a delta P. So in this case, our specimen, it looked like we probably, we came to equilibrium at 9,250 kPa, so 9.25 MPa. And then on the top side, we created a delta P of about 500 kPa. So we just dropped the pressure on the top side of the specimen and then watched the pressure from the bottom side propagate through. And you wait for decay. So in this case, complete pressure decay in 20 minutes. Nice as I said, we plot temperature because we want to see, or we're recording temperature. So this is the temperature change inside of the system, plus minus probably 0.05 degrees Celsius. And if I use that equation, get a change in pressure inside your specimen of plus minus 5 kPa. So very low, not going to affect your result too much. So this system, and that's over a 20-minute period. So the system design, we really paid attention to keeping temperature as constant as possible. So we apply that pulse by dropping the downstream and then monitoring, or dropping the upstream and then monitoring the downstream. And we get a result of 400 nanodarcy. Interesting response right here. So we'll talk about that. But this is the basic equation. So everybody is very good at differentials in math. So the basic equation here, Darcy's law, you have a specific storage term and a hydraulic conductivity, which is permeability and viscosity and fluid density. So that is what appears in the equation. And when you're doing a transient solution, you're solving that for both. You can make some assumptions and cancel some, or say that this term doesn't impact anything. So specific storage, what's in there? Density of fluid, gravity, porosity of your fluid, compressibility of the water, effective bulk compressivity, and the grain compressibility. All of those are your poroelastic constant terms. Part of that, very difficult to measure. So you can do some simplified things and say that my specific storage is equal to 0. So you assume that your porosity is very low and your compressibility is very low, and that they essentially contribute nothing. And then you can come up with a pretty straightforward equation, and your solution looks like so. So this is just plotting that solution using some input parameters from our testing system. And the other thing you can say is, so this is Brace 1967. He kind of started this technique, and it's kind of the original reference for all this stuff he worked on westerly granite. And then in 1981, Hsieh et al., the other kind of reference to follow here, said, well, let's say that there's homogeneous storage, and included the storage term, and then your solution looks like this. So there's a whole bunch of solving you need to do in there. So some numerical approaches to solving that through iteration. But your response for the exact same data in the exact same testing system look like this. So here is the pulse. This is the solution from this data set. So it's the same data. It's the data with the solution attached now. So this is what the solution looks like. This component up here, this is the storage component of the system. So the specific storage component, sorry, not of the system, the specific storage of your rock sample. So you apply this pressure transient, and there's a delay until the response gets to the other side. So that is the storage component, and then you come to equilibrium. So you can see two completely different signatures for the exact same specimen, exact same test, sorry, exact same input parameters into the solution. So this is our experimental setup. One of the experimental setups, we made a modification. But what you're trying to do is, when you're doing this test, you want to minimize the upstream volume and downstream reservoir volumes. So if I assume that they're both equal, you can pretty much make them equal in the laboratory. The smaller that reservoir volume gets, the lower the permeability measurement you can make. Again, time is your biggest enemy, because the longer the time is going for your test, the longer the specimen's in the system, and the more temperature may come into play if you do not have extremely good control on temperature. So this direction here is decreasing permeability. So the top one is 1 nanodarcy. So if the smaller you can get this volume, you can get your test time down to 10, 20, 30, 40 hours for very low permeability. So to get a good measurement of the specific storage, we also need to have the upstream and downstream volumes very close to the pore volume. So I look at two situations here, two specimen scenarios. This one is a 2.5 by 2.5 inch specimen, or 61 by 61 millimeters. Porosity 1%. If I do the volume calculation, the pore volume is 2 milliliters. In our testing system, our upstream and downstream system volumes is 6 milliliters. So 33%, right? We're on the same order for the volumes. That means that when we do this pulse test, we're able to, what that comes out as, you're able to actually see the storage term in your specimen. If I look at a 1 inch by 1 inch or 25 millimeter by 25 millimeter specimen, my pore volume of the specimen is 0.12 milliliters, and my upstream and downstream volume is 2 milliliters. So much larger difference. And if I just take the solution, so there's no data here, this is just plotting the solutions, the Hsieh solution, which includes the storage term, you can barely see the storage term, but there's no way you're gonna fit your data to that. This one, no problem. So you might see that in when you have to run an actual test, but it's gonna be very hard to distinguish when that actually shows up. So here's our experimental configuration. During the testing program, our client NWMO asked us, after our initial stage, they asked us, this was great, you're able to run like one specimen at a time, takes 2 weeks to do one test. We want you to do the same amount of work in like much less time. So how are you going to do that? So we built 9 of these testing cells, 9 of these testing cells. So 3 testing cells each inside of one oven. They all have data loggers and independent data loggers, 2 pumps. So we're sharing the pump for the confining stress and the pore pressure. Everything's put inside the oven. All of our valves are servo controlled. So we have some great mechanical engineers and designers in our group. We were able to take off the shelf remote control servo controllers and for remote control vehicles, $35 each, and couple them to our valves, and then build a control panel so we can run everything outside of the oven. And once the test is going, we never have to open the door. When you open the door, you're changing the temperature and everything goes wrong. The other thing that we noticed, and I'm going to say we because myself, Stephen, Francy, and Hsieh, everybody else in the laboratory noticed that if you have a power supply powering your sensors and you have longer leads going to your sensors, that's a big, long resistor in line. So if the temperature in your laboratory starts fluctuating, the actual power supply to your sensor changes. It's very small. The resistance in your lead changes. If you're looking to measure like really small values, all of that comes into play. So you can plot, like if you have temperature and resistance and power, you can actually see it fluctuate up and down as the temperature in the laboratory changes. So it may not impact your work, but it may be something that you might want to pay attention to, or probably pay attention to. So you can log the voltage coming out of your power supply and log the temperature in your room. and see how they correlate. Here's our testing system. So the experimental system, the orange line is the confining pressure, and then the green line is the pore pressure. So on the bottom, we have a valve, a pressure transducer connected to the specimen on the bottom side. So P7 is the bottom valve and bottom pressure transducer. And on the top side, P8, kind of cut off there, you can see the line flowing up to the top of the specimen. And we have a valve on both sides. So we're able to load a pressure pulse behind one valve, use our servo, click it open and click it close, and that introduces the transient. So there's valve, servo controller, and then you can see the pressure transducer at the bottom. So the goal was to make this as small as possible so we could reduce the testing time as much as possible. For the 25 millimeter by 25 millimeter specimen, we were able to get it down to 2 milliliter dead volume. And then for the larger one, 6 milliliter for a 61 millimeter by 61 millimeter. One of the bigger contributors to the volume, or a contributor to the volume, which we're looking at removing, is the porous plate that we put across the bottom. May not be necessary, but we used it to make sure it diffuses the pulse across the bottom of the sample, so it uniformly flows across. The other thing, and I'll talk about this, that is a problem, but it's not a unsolvable problem, is everything I've talked to so far assumes that we can do our best on temperature and minimize all of our volumes to do this test, which is great. But when we're measuring very small pressure or pressure changes over time, leaks always are a problem. So you assume that there's no pressure leaking out of any of these 12 connections, 8 connections in the line between the valve, the transducer, and the specimen. So if you can weld as many of those fittings as possible, that would be the best approach. There's always trade-offs, because if the fitting breaks or something, then you have to go and re-weld the entire system. So you want to weld as much as you can, but make sure that you can not spend too much money if something breaks down. What you see sometimes people doing in a transient approach is putting a delta P transducer also in the system. So what is this actually? How does a delta P transducer work? It has a diaphragm in it, and it's just a strain gauge diaphragm. So as you deform it one way or the other, that's what says there's a differential pressure on there. What that deformation actually does, Stephen calls it the hammer technique or hammer response. So if you apply a pressure up here, you're going to hit your delta P transducer with your pulse, and then you'll see a reflection through the other side, and then it comes and hits the other side of the sample. So now you're pulsing with a big pulse at the bottom and a smaller pulse at the, sorry, a big pulse at the top and a smaller pulse at the bottom. That's going to impact your test. You can solve it with the solution. You generally just don't want to do that. The other thing it's doing is adding an additional upstream and downstream volumes. So your tests are going to take longer if you do this. So just in general, we remove that delta P transducer and don't use it. So here is a result using some real data. The solution is the dashed lines, and the data is the solid lines. This is just a 61 by 61 millimeter specimen. The blue here is, this is the real data response. So if you're using the brace solution or any other solution, you can plot the differential pressure and then solve your, match your analytical solution, the brace solution or the Hsieh solution to your data by error minimization. And then that's your permeability result. So you can solve only using the delta P. If you have a delta P transducer, or let's just say we're never going to use a delta P transducer, so you just take the upstream and downstream pressure and subtract them to get the delta P. So you can fit the delta P and it looks really nice. But if you're not monitoring or looking at the upstream and downstream, this is what the data actually looks like. So here's your data, and the dashed lines, this is the brace solution plotted in upstream and downstream pressure. So same solution, it's just one plotted at delta P and one plotted upstream and downstream. So sometimes this can be good enough. Our permeability is 86.3 nanodarcy. I think minus 14 meters per second, in that range. This is what your response would look like. But if I use the Hsieh solution, so this solution assumes that the specific storage is 0, right? That's the brace solution from 67. If you use the Hsieh solution and don't assume the specific storage of the sample is 0, then you simultaneously use the pressure, the equation at the top, the Hsieh solution to calculate the pressure at the top and the bottom, and numerically match that to your data response. So again, the data is in the color lines, and you get a pretty good fit. And I can plot the same one with the delta P. So there's the specific storage term. You can see the delay in the response after the pulse. That's just the storage. And you could do the same thing plotting delta P. So the Hsieh solution gives you 83 nanodarcy and the brace solution 86 nanodarcy. These numbers are very close, but depending on your client, those numbers are different. Temperature, because this is all about temperature in the laboratory. The Hsieh solution, again, 83 nanodarcy specific storage. Let's look at just this misfit down here. Just this misfit. So we plot, as I said, we're plotting temperature. So this is how temperature fluctuated during the testing time. So probably better to plot delta T, but we're plus minus 0.05 degrees Celsius throughout the entire length of that test. And if I go to the plot over here, this is temperature in blue. The red is the pressure created by that change in temperature. And if I look at the top and bottom solution, the misfit between the data and the actual solution, you can see that it tracks pretty well with how the temperature is changing. So that small amount of temperature change during that testing period is leading to less than ideal, less than ideal test. You can say a perfect test would match my analytical solution or the Hsieh solution perfectly, but some transients in there causing that issue. The other thing I talked about, leaks. So small leaks can become a problem. And if you don't handle them a little bit, then you cannot fit your term. So this is another test. This is probably 1 inch, a 25 millimeter by 25 millimeter test. There is the data in the color, blue and green, and then the solution in the dashed line. So the solution says it should come to equilibrium. This one is trailing off or upwards. So there's a leak in here. And because we're using, we kind of said that most of our leaks are probably from the confining pressure leaking into the sample, either through the top, bottom, in the middle somewhere. But the pressure is going up. So it should come to equilibrium. This one's going up. So what we can do as a first order approximation is estimate that leak rate just by drawing a line through it. And as it comes to, as we trail off in time. So if I can make this a straight line, then I can estimate a leak rate on the top of 0.129 kPa per second and a bottom leak rate. And I can say, well, I can kind of measure the leak rate because I'm way off at equilibrium, and I can just see the leak and that's it. So if I do that, then I can subtract the top leak rate. So subtracting the top leak rate, then if I just fit the brace solution, I'll get 13.8 nanodarcy. So it looks like that. So you can get a pretty good approximation. This is with the brace solution. So as I said before, the brace solution, you're assuming the storage is 0. So if I look at my data, I can see no storage response. So I can say that my brace solution is close enough for this test. And with the brace solution, because I have no storage, I can just use the delta P to do my calculation. And with that, I can get a nice fit, and brace solution 13.8 nanodarcy. That's my simple approach. Stephen likes to be a little more rigorous with the math. So he says, let's just introduce a source term. So the math looks like so. And if I introduce that source term, then my solution now has that source term. And I can fit that solution with the source term to my data. So instead of drawing a line through it, I can actually enter in the source terms into the solution and fit it much better. So with a better solution, with the better solution, we hold the leaky brace solution, the actual, I do that wrong. The better solution is 14.9 nanodarcy. With no accounting for the leak rate, 15.7. If I just fit to the delta P, right? Because if I'm leaking from both sides, the delta P is going to be the same. 15.7, and my first order approach of just drawing a line through and subtracting it, 13.8. So again, those are all close numbers, but they're all different numbers. So our next approach that we're using, this is some future work that Stephen's working on, and everybody in the laboratory this is the leaky brace solution. There's no storage here, so we're working on what we call a leaky Hsieh solution, so we can account for the storage. The math is much more involved, and that should be coming out. You're going to do that for ARMA, Francy? No? Okay, so that'll come out maybe next year for the work that we're doing. A really nice way to plot this test while you're doing the test is to not plot with time, but plot bottom pressure versus top pressure. So you can do this while you're doing the test, but I also use this while I'm doing the data analysis. You can tell if you have it's really easy to see if you have a leak in your data. So two tests, the one on this one here, there's no leak in this data set, and the one over here, there's a leak in this data. You can tell it long term, but if you plot top pressure versus bottom pressure, you can see the initial vertical line or vertical response is just the storage term. And then the linear component is the exponential decay. And then if it trails off, if it deviates from linear, that means you've got a leak. So really easy plot to do while you're doing the actual testing. Lots of experimental programs. Always there's assumptions, so it assumes that the specimen's continuous, homogeneous, isotropic, and linear elastic. There's no like hysteresis. The specimen is 100% liquid saturated. And if you want to ask about how we do that, we can answer that. Answer that with no proof, I guess. But we do some pretty good evacuation, and then flowing through a CO2, and then strong vacuum saturation. Other issues: sample creep, membrane compressibility, right cylinder tolerances, and you want to minimize any damages on the chips and asperities to create chips and asperities. Some future work, we're looking to strain gauge this while we're doing the test, so we can get after Biot's coefficient. So you can imagine if you're applying a pulse, you can watch a decay, and then you can apply a confining stress, which would also induce a poroelastic response. And if you measure all that stuff, you can get at Biot's coefficient. There's been I think a thesis published in 2006, and a whole bunch of work that we're going to try and implement in the laboratory. Just a nice experimental configuration. So with this system, it's really nice if you have the time to do a really good job on your CAD, because you can streamline your system, make it very efficient for your end users, and cram as much testing into a small space as possible. So this is what it looks like in the laboratory. If anybody wants to have a look, you can contact myself or Babish or Hope by email, and we can give you a quick tour. Here's the team. So Francy, Stephen, Jacob, and myself, we did most of the design. Martin did automation, which is all the servo controllers. Thomas did the logging, and Rick got us the project and all the money to do all of our work. So this is I just want to circle back to one thing, because it's sort of important. We have a good picture, and I forgot to talk about this and add it in explicitly. Okay, the storage term. So this is really nice. It shows up in the test when you do a really good job of your test and you fit your data to include a storage term. But when you actually run a test, like it's the storage term of the sample. I wonder if I can find a picture. I might not be able to. This is good. So on the outside of this, in this CAD drawing, there's no membrane on the sample, right? So you can imagine there's a latex membrane on the outside. So when you run your test and you can extract a storage term out, it's the compressibility, grain compressibility, bulk compressibility, water compressibility. What else is in there? The membrane is actually part of that storage system. So you can't just do your test and say this is the sample storage, because it's almost impossible to back out or extract the membrane compressibility from that. So if you're doing this type of test, just understand that that specific storage term really helps to, it'll help you to get a better measurement on permeability, but the specific storage term is not fully a property of the specimen. It also includes the membrane. Is that roughly okay? It's roughly okay.
Thank you very much, Dr. Nathan. Any question? A moment first. Yeah, perfect.
Just a quick question while we're on the topic of the storage. So in your experimental data, are you actually able to see that storage in some tests and not in others? So specifically where you're able to fit the very solution?
Yeah, so excellent question. So when the specimen is larger, so we tested 2 specimens for this program, 1 inch by 1 inch and 2.5 inch by 2.5 inch, 60 or 25 by 25 by 61 by 61. So as soon as our pore volume became close to our upstream and downstream storage volume, we are able to see that signature. If it's too low, you cannot see that signature, right? You have like either like a very small volume on one side or a lake on the other side compared to the actual storage of the specimen. So if I look at, so this is real data, okay, in the color lines, you're able to see the storage term here. And this is real data. So that one I just showed, that was 61 by 61, this is 25 by 25. So we're definitely, you can sort of see it, but it's not like prominent in the test.
Yeah, that makes sense.
Yeah.
Sample size. So if you were able to, so if you're planning on getting rid of that porous stone, then how would you make sure that you're actually getting the distribution?
Right.
Okay.
Yeah, no, that's the question, right? If you want, like, what more can we do to reduce the storage volume or the upstream and downstream volumes in the reservoir to get like the right response or a good response out of the system, okay, without compromising the entire test, right? There's all of these other issues, like, are we channeling up the side? Like, we're assuming a uniform pressure front through the specimen, which is, you know, you kind of have to do that.
Very interesting. Yeah, great presentation.
Thanks.
Thank you very much. Any other questions?
Yeah, it was a great presentation. Just like, is there a different configuration? Like, could you say drill a small hole in the top of the sample and then at the bottom of the sample so that you're only injecting once within the sample itself as opposed to the ends? Or not familiar with Brace's original test.
Oh, Stephen has an answer.
You can do that, but essentially this is a filter form analytical solution. And in Excel, that one will have the analytical solution. Solving it. One could. But yeah, it's not in Carlso and Jaeger, then it's hard.
Any other question? Just one question regarding those tests as 1 week or so. How is the quick behavior, like in those little measurements of permeability, the quick behavior during that week impact? Do you have the impact of the temperature? I don't know if you have the chance to at least once measure the quick behavior and try to correlate how much of that quick behavior during that week impact the final result.
Yeah. Really hard to answer until we put a strain gauge on the specimen. The test does assume that it's linear elastic, so we load it and everything's stable. All the tests that we're doing, we are using in situ stress conditions. Yeah, creep, unsure. The other important part of what you just said is this test looks really nice. It took 6,000 seconds to complete. How long did it take us to get to a point where we could run a test? About 7 days, right? So seven days for 10 days. Where first we load it, then we, the specimen's first completely vacuum dried, so there's no water in there. Then we put it in the cell, we load it to about 500 kPa effective stress, sweep it with CO2 to remove any air. Then we vacuum it on both sides to get as much out as we can. And then we apply water pressure on one side, holding a vacuum on the other side. And then Stephen and Francy monitor the vapor pressure on the vacuum side, and then continually apply small pulses of water until we think we've got it mostly saturated. And then we put the pore pressure all the way up to 10 MPa and let it sit for another 3, 4, 5 days. And then we say, we think we're saturated, and then we run a test, which takes 20 minutes, right? So lots and lots of work to get to a state where we think we're at satisfied all the assumptions of the test.
Well, it's just a comment, like this whole business of really tight materials, the rock, is always a challenge, right? What is the actual in situ conditions? Because you're still testing samples that came out of the ground at some considerable depth.
Yeah.
And so volume expansion that takes place, and no matter how much pressure you put to it, you're never going to recover what took place getting a sample out of the ground.
Yeah.
So your solution is still maybe it still be on the low side. I mean, it still may be tighter in situ by a significant amount.
Yeah.
Considering those small changes in permeability.
Yeah, you take it out, you unload it, and you have cracking on the grain boundaries. And we've even seen from drilling, we're testing the 61 by 61 millimeter core. That's the same size that they're cutting. So we just take that and test that.
Right.
Well, did you do any damage on the boundaries when you're drilling?
Oh, absolutely.
Yeah. So.
Yeah, absolutely. I mean, the work that they did at ACL when we were down at 240 meters, and we first started getting water coming out of the fault zone, which had geochemical signatures, which were indicative of millions of years old. And there was just, when they tried to reconcile the permeability of the core with the geochemical signatures they were getting in a fault zone, it didn't even make sense.
Yeah.
Just showed that water be trapped in these rocks a very long time. The salt content of rock body was 3 times saltier than seawater. So permeability is pretty low.
No, I remember we asked when we ran a pulse, and it just flatlined, right? We couldn't get a pulse from one of the systems, and we said it's 0, and somebody said, well, no, you need to do better than that. We need a real number. Or no, less than what we can measure. Yeah.
Very good presentation. I just have a question, a high-level question. When you have permeability this low, what is the significance of those permeability varying by 10 or 20% up and down in the grand scheme of things? And especially considering, I think, the faults and the geological controls where you have in this range, aren't they going to control your flow and more other things anyway?
Yeah, I mean, Professor Mart would know much better this answer, but from what our clients are asking for this program, they're looking to model out to, I think, 100,000 years, maybe longer. So when your number starts varying by 20, 30%, right? But that model response is much, much larger. But I think 100,000 years for NWM or something, right? What does that number mean? So no, like I said, for most of us in the work that we as geotechnical engineers, it's the same number, right? Yeah. 14, 15, 16 nanodarcies. It's zero.
You know, it does have lots of geological significance because you take southern Ontario, and southern Ontario has a huge basin of sedimentary rocks, which are in the order. And when they were installing the West Bay Packer system, you know, it was going down 1,000 meters. Right? What they found was that the oil pressure, because you got Lake Ontario above it. So you have a lake up there. And then you would think it's fully saturated going all the way to the Brigade, which is down where you can measure Lake Ontario. But what they found was that oil pressure started to go down, down. So when they got to an area in the shales, which were about 250 meters in section, the under pressure was so significant that they thought they were going to collapse the casing. So then the question is, how does this geological formation hold this under pressure at these depths? And if you have any geological fault, it doesn't work. Just like you said, you know, fault takes care of all the pressure. So it tells you right away there are no faults in that area to hold that pressure. But then the question was, so is it related to glacial unloading, or is it related to the removal of the sedimentary rocks back 400 million years ago? And I don't think they could ever resolve it because they're down into the testing ranges of mercury.
Yeah.
But it's definitely older than the glaciation. But when they actually have to tell you why they're unloaded. But that massive rock, even though it's only down 400, 500 meters, has not adjusted to the unloading that took place at least 100,000 years ago. No, it's when you get this kind of information, you know, like a lot of things that we assume, and now our information, our instrumentation is so good in situ that you can get the pieces together. And predicting out to 100,000 years within the realm of reality, but it becomes a little more believable. Because you have geological evidence that that system has been stable for at least that long.
Thank you very much for coming today.